We want to now look at what we call the cyclic quadrilateral and some theorems that are involved with that. So the first one here is looking at the idea that in a cyclic quadrilateral, now a cyclic quadrilateral is one where all four vertices of your quadrilateral sit on the circumference of a circle. Now when that happens, we get some nice little results happening. And the first one is that we can get the opposite angles in the cyclic quadrilateral will be supplementary. So if you have a look at this angle here, 80.17 and 99.83, if you add those together, 180. There we go. If I start moving around one of the other vertices so the angles change, so we're starting to get 100.28, 79.72, add them together, we get 180. So it doesn't matter where they go, the two angles will always add up to 180. And if these two angles add up to 180, then these two angles must add up to 180. So we get the idea that the opposite angles in a cyclic quadrilateral are supplementary. The proof of that comes here. So we have the proof here where we're looking at A, B, C, D being cyclic. And if we have a look at getting our radii here and just constructing OB and OD. So if this angle here is X, then by our rule where we had the angle at the center is twice the angle at the circumference standing on the same arc. So our arc BD, that way the major arc, we get that being 2x. If we let this angle here be y, then again the angle standing on the same arc is angles on the arc is at the circumference standing on the same arc is twice the angle as the angle at the center is twice the angle at the circumference. Let's get that right. And this time we're using the minor arc BD. So there's our rules there, and this is why we get those angles that way. Now if these two angles add up to be 360 degrees, so 2x plus 2y equals 360, because it's a circle, it says angles around a point, we could say it's a revolution as well. So but the two angles there go around one point completely, so they must add up to 360. Divide every term by 2 gives us x plus y is equal to 180 degrees. So there's those two angles which are opposite angles in the cyclic quadrilateral. Then they must be supplementary. There we go. So there's our proof, and because those two are supplementary, the other two must be supplementary. If you want to prove that, you can construct the radii to OA and OC and then prove that. But well, there's only two other angles in your quadrilateral, and we know that the quadrilateral has to add up to 360 degrees in its angle sum, so the other two must add up to 180 as well. So there's that rule. Now the other one that deals with a cyclic quadrilateral is the one where we have the exterior angle. Now we've got an exterior, what we call the exterior angle is if we get EF and produce it from the cyclic quadrilateral. So it keeps going on. So I've got a point G here, so it goes to G, and it can go on forever. But it's just that it's that side being extended. Now, what you notice, the two angles here are giving us the same value. So it doesn't matter where we go with our point and change the angle, we start to get the same values for our opposite, our exterior angle and the opposite interior angle. So we can see the the angle opposite there. So the exterior angle opposite is equal to the opposite angle in the cyclic quadrilateral. And the proof's pretty easy, because if these two are supplementary and these two are supplementary, then they must both be supplementary together. So that proves not too hard. So B and ABC and ADC here, we know are cyclic, because it's a cyclic quadrilateral, are supplementary. They add up to 180, and these two are on a straight line, so they add up to 180. So that means these two must be equal, because they are adding the same angle together to give you 180 degrees. So they must be equal there. So that's not a hard proof when we know that the two angles are supplementary. So there's the two theorems that we deal with cyclic quadrilaterals. Now again, if you have a quadrilateral that does this, then it must be cyclic, and the same with these if you don't have the circle, then you don't know it's a cyclic quadrilateral. There's your proof that you have 4 points that will form will be on the same circumference of a circle, because if the opposite angles are add up to 180 degrees, then the 4 points of that quadrilateral must go through a circle. So things like a square, rectangle, because they're the easy ones we know add up to 180 degrees, because they're 90 degrees on each corner. Then they always have a circle going through them. So they are the easy ones to follow. So there's our two theorems. Keep them in mind. The ones with cyclic quadrilaterals, because there's only two of them, it's not too hard to pick them out a lot of times when we see a cyclic quadrilateral or given a cyclic quadrilateral in a proof.